Last time we talked about, we kind of finished this LQG story that was sort of told in two parts by talking about the Kalman filter. And, this whole idea of separation principle, and you can stick the Kalman filter and the LQR controller together and it's optimal and all things are nice. And then we talked about, basically we do that all the time, even if it's not optimal on nonlinear systems. And then the kind of last little nugget in there that I threw in was this idea of duality, which is a really interesting sort of set of ideas around the fact that state estimation, filtering, et cetera, is dual in like a deep mathematical sense to control, and how you can basically like remap one into the other with some little changes of variables and stuff. And it works both ways. And so in the linear case, basically the Kalman filter and the LQR controller are really the same thing. You flip around some matrices and run time the opposite way. And it also generalizes to the nonlinear setting. So like map estimation is, you can write it as a trajectory optimization problem. And this actually works out. There's sort of state estimators that look very much like MPC, where you solve optimization problems online, all kinds of interesting stuff. Cool. So that's the end of that. And today we're going to switch gears again. For kind of another sort of very classic control theory topic, which is robust control. And we're going to sort of ground this in a particular algorithm that sort of, very much following the arc of the class, which is called Minimax Differential Dynamic Programming, DDP. So there's like a really fun little like quote that you can solve basically every problem in control with LQR. This is yet another example of this, right? So like stabilization, tracking, trajectory optimization for nonlinear systems with iterative LQR. And it turns out here you can do, like with another extension of LQR, basically you can do robust control. There's like Minimax LQR DDP type of idea. So, and also state estimation, right? The Kalman filter is basically LQR the other way around. So you should really spend some time with that one. It's a really powerful idea. All right, cool. Any questions about any of that? All right then. So to start off with, I want to just kind of contextualize and comment on some of these ideas, right? So last time we talked about this whole set of ideas around stochastic optimal control, right? And the idea there is, you're assuming that there's random noise in the dynamics, right? And in the measurements and all this good stuff. But there's some strong assumptions baked in there. In particular, in the sort of LQG setting, we're assuming that the noises are all zero mean and Gaussian, right? And the thing that's, I think, important to realize there is, it is very common in practice, and you are frequently tempted to like wrap modeling error into these noise terms, right? So you can say, oh, I have process noise. Whatever is wrong in my dynamics model, I'm just going to sort of inflate the noise and treat it as noise. But that can be a bad thing in a lot of situations. And kind of the main reason why is that, Gaussian zero mean noise, it's got this, kind of average out to zero property, right? Whereas model errors, like you can imagine if I have parametric uncertainty in my model, let's say like the mass is off by 10%. That does not look like zero mean noise at all, right? It looks like a bias that's pushing you in one direction. And that's frequently the flavor of these parametric uncertainties. And this whole like LQG setup does not work there. So if you like have a constant bias sort of thing in one of your model parameters, it means you do the kind of standard LQG thing and you think, oh, I'm going to just wrap this 10% uncertainty into my process noise. It absolutely doesn't look that way. And you'll get stuff that does, this and sort of drifts off and eventually blows up, right? So these are different things, and you can't think about these sort of model errors typically as process noise. That's sort of the main point there. So stochastic things, assume, So sort of the stuff we talked about last week, they assume random noise, and in particular, right, they're assuming this noise is, basically another way to think about this is the noise is you're drawing new noise samples at like every time step as you run the system. Whereas in this sort of robust context, we're assuming like, okay, there might be like, you might model these things as set value to random, but the idea is, you know, for a given system, you're going to draw once and it's going to stay like that for all time, which is a very different idea, right? So LKG assumes noise is zero mean. This is not a good model for sort of parametric uncertainty. Okay, sort of the first important idea. So these are different ideas. You can't just treat these things as noise as the kind of main thing. And so other ideas we talked about that sort of get at this, that we've already talked about, ILC, right? This sort of idea, I would put ILC under the general category of adaptive controls. The idea is there's some model mismatch. I want to get the optimal answer. I'm going to sort of do some data-driven stuff, run some rollouts on the hardware, and adapt my control policy to the specific parameters of that robot, right? So that's adaptation. If I go take that thing and run it on another robot that has slightly different parameters, but it was dialed in on a different piece of hardware with slightly different parameters, it could just blow up on the new robot, right? Okay, so that's adaptation, adaptive control. And the ideas there, I would say adaptive control, you're really trying to achieve super good performance. You're trying to be optimal by using data online, right? But the sort of strong like philosophical bias is performance. Okay. So those are kind of two things we've talked about so far that, you know, get at what happens when the model's bad, et cetera, right? Okay, so robust control, I would say, is coming from a very just philosophically different place. It's not random noise, and it's not trying to adapt online like ILC or some other adaptive controller. It's not trying to figure out what the bad model parameters are to online. Instead, it's taking this like uber conservative approach. And what you do is you try to bound the bad things offline. So you say, okay, here's my model. I think there's 10% uncertainty in these parameters, right? And then what you do is try to design a single control policy ahead of time offline that does not adapt. That's this one policy that's going to guarantee stability of any particular system within that set of bounds, right? So say I have 10 robots and there's 10% variation, right, due to manufacturing weirdnesses. Or I have, you know, some quad rotor and I know there's going to be wind gusts, but I can bound how big they're going to be, stuff like this, right? So you're not going to try to figure out what those parameters are or estimate the wind online. You're going to design a feedback controller offline that says, given these bounds, I guarantee that this one controller will work across that whole range of robots, parameters, whatever, and give me reasonable performance, right? So that's sort of the big picture idea. It's like a design once, don't adapt, but be super conservative. And at the end of the day, there's a trade-off here, right? So in exchange for that robustness, you're almost by necessity giving up some performance, right? So an adaptive controller, the idea is you're going all in on performance. You're trying to estimate the stuff out online, figure it out so that ultimately you can achieve low cost, high performance. In a robust setting, you're going to basically say, I'd like to achieve this level of performance, but really I need to achieve the best performance I can across any possible realization within the bounds. So you're going to end up at the end of the day doing worse on your performance metric in order to achieve that level of robust stability across all the possible models. Okay, any questions about that sort of set of ideas? try to design a controller offline that will still work, i.e. be stable. That's usually what we care about. Under a range of different possible models. And generally, you're sacrificing some performance for this. Okay, cool. Questions about that? So that's like the big picture idea, right? So we've talked about stochastic stuff. We sort of talked about adaptive stuff. This is a different idea, and it's sort of the most conservative flavor of this sort of set of ideas. The history on this is super fun. I think I teased this previously. Oops. So if you look back at the history of control, early work on LQR showed strong robustness. Like basically, if you do full state feedback and you just have an LQR controller, people actually proved robustness guarantees for vanilla LQR. And so people thought that LQR was sort of magic and had these natural robustness properties, and we didn't have to worry too much. And if the model was a little off, LQR was still going to be fine. But then it turned out later, it was discovered that LQG, so where you hook the Kalman filter up and do state estimation and feed it into the Kalman filter, like we talked about last week, is arbitrarily fragile. It turns out like epsilon perturbations of the linear system that you're using, those ABC matrices, can result in an unstable closed loop system in that case. And there's a super famous paper by John Doyle that I think I showed previously that, let's see if I can find it here. I had it saved to show again because it's super fun and you should know about it. It's one of the all-time classics. Where'd this go? Here we go. So here's the classic John Doyle paper. I think this is from like 1978. Guaranteed margins for LQG regulators, abstract, there are none. And it's like a 1.5-page note that I think he wrote as a grad student. And basically the whole thing is he just came up with like a couple of little counter examples showing that if you put a tiny epsilon, arbitrarily small, into the ABC matrices, that that little epsilon, infinitesimal epsilon will drive the closed loop unstable. So kind of crazy, amazing paper. It's it's super short and it's super easy to understand. And you should check it out. And this paper in the late 70s spawned the entire field of robust control theory, which was a huge deal and basically what everyone was doing through the 80s and into the 90s, sort of early 90s. If you went to grad school in the 80s or 90s for control, this was basically what everyone was doing, was kind of linear robust control and trying to figure out how to guarantee that the system wasn't going to blow up under sort of bounded model uncertainties and stuff like that. Super cool. Check the paper out. I'll post it on Piazza. If I don't, someone bug me. Cool. So any questions about that sort of stuff? The intro. Cool. So interestingly, there's deep connections. Has anyone taken like an old school frequency domain CISO control course with like Laplace transforms and Bodie plots and all that stuff? So it turns out that the modern theory of robust control for multivariate systems, actually, there's a lot of throwback ideas in there. And it's quite closely related to old school frequency domain ideas, which turn out to be quite robust. So if anyone, when you did those like old school CISO Bodie plot ideas, remember phase and gain margins? Basically what happened in the 80s and 90s is people went back to sort of that flavor of idea and tried to figure out how to get those kind of margins for multivariate linear systems with state estimation and stuff. So that's actually the flavor of the ideas there. And the general theory is called H infinity control, if anyone's heard of that. But it looks surprisingly like 1920s, 30s vintage CISO control. Okay, so LQR. But later, John Doyle showed us that LQG, which is what we talked about last week, and be very fragile. Cool. All right. Everyone cool with that stuff? No, not noise, model error. So if I write down my A and B matrices, right, for the linear system, ABC, right, measurement model and dynamics, if A is a little bit wrong, for example, right, and there's some perturbation, to the system dynamics, right, which corresponds, right, like I got the length wrong or the mass wrong by like a few percent. That's what we're talking about here. So we're not talking about noise. In fact, for linear everything, right, LQG is optimal and the best you can do, right? And you can jack up the noise really high and the performance will get bad, relatively speaking. You'll get higher cost, but it's the optimal thing. It's the best you can do, and it's not unstable. Whereas we're talking still in the realm of linear systems, right? You can write down a linear system, ABC matrices. If I perturb the entries of the A, B, and C, right? So make the dynamics or the measurement model slightly different. If you're doing full state feedback, so it's just A, B, and you're assuming you get full state measurements that are perfect, classical LQR, it's quite robust. You can like add lots of perturbations to the A and B matrices and it'll still be stable. But in the sort of partial state observation, noisy case, the LQG case, where you have ABC and you have a Kalman filter and an LQR controller hooked together, if you perturb A, B, and C, if I add like perturbations to the system matrices, right? So like I design on a nominal model, but then I simulate with a truth model, that can be super fragile to small perturbations in A, B, and C. So small model errors, extremely small model errors. In fact, in the John Doyle paper, he shows like infinitesimal model errors can cause an unstable closed loop system on it. So it has like, you should check the paper out. It's actually very easy to sort of see what's going on there, but it comes down to the fact that like you're not really measuring the full state, right? So you might only, for example, be measuring like positions, right? And then the filter has to like infer the velocities using the dynamics model, right? And then that expected, full state gets fed into the controller, right? So it at a deep level, it has to do with that, like that you're you're also reconstructing the state from partial observations using the dynamics, right?
We're getting at it, like
basically like the model errors are messing up your state estimate. And then that's what you're doing feedback on, and your feedback gains are also messed up a little bit, right? And that it turns out that when you're doing the full loop with the state estimator, you can end up having a very sort of fragile thing that goes unstable very quickly. Yeah, and again, the paper just points this out with like a quick little couple of toy examples showing that this happens. But it gives you some insight. And then later, there were like 20 years of work on this, trying to fix this essentially. Which, yeah, there are whole courses in this. There's a MATLAB toolbox for this, all this good stuff. Okay, cool. So let's sort of define some stuff and lay out the problem. So the typical robust control problem is assume we have a system that looks like the following. So our classic, let's say discrete time, and we'll do nonlinear. So we have our usual f of x, u, and now we're going to add a third input that we'll call w. This is not a process noise. Sorry, I'm recycling the letter. We're going to call, although it could be, we're going to call this the disturbance. And this can be literally anything. It can represent sort of, uncertainty in the mass, right? So like W could have like a delta M in it. It could have like, perturbations to all the model parameters, the lengths, stiffnesses of the system. Could be disturbance forces, right? So like if this were a quadrotor, it could represent wind, steady wind or a gust, pretty much anything that you can think of that might mess up the system. You can kind of bury in that W, right? And it doesn't have any particular properties here, right? It doesn't have to be zero mean Gaussian. It doesn't have to be anything. It can be whatever you want, right? So it's a lot more general in some sense than the stochastic stuff we talked about last time. So it could be, say, constant parameter offsets. Could be time varying stuff. Could be non-smooth stuff like stiction. Could be bounds on your prediction error from your state estimator, say. Pretty much anything you can think of, right? And then sort of to actually get anywhere, to make this a tractable problem, because if W can be so arbitrary, I mean, if W can be huge, then it's almost like, what's the point in having this model anyway, right? What good is it? It can't really do anything. So to actually make any progress on this, the typical assumption is that W has like a bounded norm, or like is drawn from a set of, finite set or something like this. So let's write that down. So it's got to be bounded really to like make any progress. So for example, like bounded norm, right? Something like that. So that's the model, that's the context. And then what we end up trying to do to like solve the control problem is there's many ways to do this, I should say, but this is a pretty standard approach that I would say describes much of the literature. We have a problem that looks like this. So we're going to do our typical min over x, say, and u. And we're going to have our cost function that we are used to, right? So I'll write this kind of in a pretty general way. So we'll have like our stage cost. And it's going to maybe depend on W. And then we'll have our terminal cost. So we're going to minimize this guy subject to our dynamics and stuff. So we're minimizing with respect to X and U, but we're going to maximize with respect to W. So the interpretation of this is we're trying to do the best we can with our controller, right? We're trying to minimize the cost with respect to the U's. So our controller is trying to do the best it can, given the worst case W's. So this is kind of, again, going back to this philosophical idea of trying to be conservative, right? So the idea here is I want to make sure the system doesn't blow up in the worst case. So whatever the worst possible W I can pick at a given time, I'm going to assume that W, and then I'm going to make the best of the situation with the controller. That's sort of, does that make sense to everybody? Okay. So has anyone ever seen an optimization problem that looks like this? Yeah, so we talked about this with the Lagrangian thing. This is called a Minimax optimization problem. And it's just going back to the Lagrangian idea, what kind of optimum are we finding with this thing? It's a saddle plan, that's right. So it's a minimum with respect to the X's and U's, and it's a max with respect to the W's, right? It's always a saddle point. And just to flesh this out, we've got our dynamics. And then we've got constraints. So for example, this would be like, the usual stuff. So we'll assume like maybe we have some state constraints. So X is drawn from some set. We have control limits. So written abstractly, right? That's like U is drawn from some set. And then, like we said, to make progress on this and make it make sense, we're going to end up trying to put constraints on W as well, i.e. assume W is drawn from some set, right? So it could be, again, a norm bound or whatever you want, right? Although, there are options that are easy mathematically and options that are intractable and hard mathematically. So that's the general idea. Yeah, curious, so we've seen this in the Lagrangian context, right? With Lagrange multipliers, this idea of saddle point, minimax. Has anyone seen this anywhere else? Yeah. So GANs, which are like the current hot thing that look like this, right? Generative adversarial networks. So that word adversarial is actually kind of key to this. So this has another interpretation, which is as a two-player game, which is basically the GAN thing as well. So the idea here is you can imagine I have a U player, a control player who's trying to, has one set of objectives, trying to minimize the cost. And I have an adversary, like a second player who's the W player or the disturbance player, who's trying to maximize the cost. It's a zero-sum game, right? So they're basically fighting each other. One's trying to push the cost as high as possible. The other one's trying to push it as low as possible. And you have these like basically two players. This could be considered, you might call this a game against nature, right? In the case where the W's the environment. But that's kind of the idea. You can think about it also as like two players playing a game, and the rules of the game are, F and J. And then they're trying to, basically each player is trying to win and do the best they can, right? Does that make sense? So yeah, this sort of idea, this is exactly what happens in a GAN with this like adversarial thing. Where else? General games, right? There's lots of other examples of game theory things that look like this, but this would be a two-player zero-sum game in that lingo. This has other things that show up in like economics and various other situations. No, yeah. So yeah, anyone seen that stuff before? Yeah, cool. Okay. Because basically like one player is trying to minimize and one player is trying to maximize. And like there's it basically one player doing better necessarily means the other player is doing worse. So there's not a situation where their interests ever align. That makes sense. So they never help each other out. It's purely adversarial. That's basically what that means. Okay, so what to say about this? We're looking for a saddle point. Where cost is minimized with respect to X and U and maximized with respect to W. And what else? So yeah, problems like this are called Minimax optimization problems. In general, these are quite hard to solve. There's a few tractable cases. So as usual, in this context, like the tractable case where we know everything and can solve everything is the linear case. So like linear dynamics, quadratic costs, right? Like there's basically a robust generalization of kind of the LQR domain, and this is called H infinity control. Yeah, there's like a MATLAB toolbox for that. 20 years of theory, and like it's pretty well understood at this point, and at least in the linear context, right? This is like state of the 80s, 90s, called H infinity control that sort of generalizes LQG. And like there's a MATLAB toolbox. It's at that level, right? It's like understood. There's textbooks on it. There's a toolbox. You just install the MATLAB toolbox and off you go. Interestingly, there is still kind of active work on this. There's some more recent work actually with John Doyle. He's still at it. called system level synthesis. If anyone's heard of this, it's kind of recent-ish, last couple of years, and pretty cool. Like another way of looking at these problems. Let's see, what else? So for nonlinear stuff, we can find local approximate solutions to this, and that's kind of what we're going to talk about. What else I want to say? Yeah. Oh yeah. This is like the two-player game thing. Okay, cool. Any questions about any of that? So that is the problem setup. If you make F like, linear, then life is good. It's non-linear, it's hard as usual.
Minimax setting, if the settings are always resulting in loss, or does it happen with the set loss?
So, I mean, there's not really, I mean, what do you call a win here? So there's like a cost function, right? And so what you end up with here is an equilibrium where basically the two players are both doing the best they can and they sort of battle it out, and then you get a cost, right? And that's the answer. So, I mean, how do you decide who wins?
Eventually the discriminator becomes better and the classifier becomes worse. So how do you?
So I would actually say there too, you're reaching a game theoretic equilibrium. They basically reach an equilibrium where everyone's doing the best they can, and that's the answer. That's in general, solutions to games are basically like, one way to think about it is deadlock, where like both players or all the players, right? If it's a multiplayer game, they're all individually doing the best they can, acting optimally, blah, 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 given the amount of information they have and the actuation or whatever control inputs they have. And then you reach some equilibrium, like stalemate, essentially, right? And that's the answer. That's the solution of the game. So that's kind of the way to think about it, right? Everyone does the best they can, and you reach some equilibrium or stalemate, if you like to think about it this way. And whatever you get, right? There are, different sort of games where there maybe is a more clear interpretation of win and loss. But these tend to be kind of like discrete games, like the prisoner's dilemma, this kind of stuff from economics, right? These are like sort of more continuous in flavor and sort of soft in some sense. And the answer is just like, there's some optimal policy with certain cost, and that's the end of it, right? So I don't know how you say the U player, the W player won, right? You just get a number for cost, and that's like the metric, right? And that's dependent on the cost you wrote down and the dynamics and all this other stuff, right? I guess you could say if you crash, the W player won, but here, right, we don't even really have a notion of crash here. It's like cost is higher. Cool. Okay, so let's see. That's that. So in keeping with like the rest of the class, so there's lots of stuff in this area. There's many, many ways to approach these problems. There's lots of different algorithms. But one sort of way to go at this is to embrace the sort of like, nonlinear trajectory optimization, DDP, ILQR kind of viewpoint, and basically take this problem that we just wrote down and like locally linearize it about a guess and do and iterate and do like a iterative LQR kind of thing on it, right? And that's what we're going to talk about now, Minimax DDP, which is actually the original paper by our very own Chris Atkinson from about 20 years ago now. It's a 2003 paper where they did this. So kind of fun. So as you'd expect, use a local Taylor expansion. Sort of iteratively approximate stuff. There's been a lot more recent work on this sort of Minimax style multiplayer DDP stuff. for general or more general games, not the necessarily robust control setting, but for driving actually, for like multi-agent sort of driving non-cooperative game models, which is kind of fun. Okay, so here's how this works. We're going to do a dynamics expansion. It's going to look very familiar. We're just going to pick up some extra terms basically associated with the W's. So we've got our F, and so we're going to do our first order thing as usual. We're going to put some deltas on here, and only difference is now we're going to have these W things hanging around. So we're going to write this as f of x u w plus a delta x, b delta u, and we'll use d for the Jacobian with respect to the w's. So that's the dynamics. Then, like before, we're going to write this in terms of like the action value function, or what you would typically call.
What do we have u plus delta x plus delta?
Oh, sorry, I'm spacing out. I had a. Thank you. So yeah, we're gonna do the action value or Q function, but we're not calling it Q because LQR and notation and whatever. So we're gonna call it S like we did before. And we're just gonna write that expansion down and have the W's in there. So this is gonna look like, again, the same kind of idea. And we're gonna end up with the sort of nominal value, the gradient, and we'll write it down, kind of separate it out. And then a Hessian term. So 1/2 delta x, delta u, delta w, and then this big Hessian thing, which we're going to write it out blockwise, right? So it's got blocks corresponding to the x and u and w sort of pieces. And it's symmetric as always. Cool. And then we're going to basically turn the crank and do the same kind of stuff that we've done before. So we're going to do the Bellman backup thing, dynamic programming thing. It's going to look very, very familiar. We just get some extra terms. So I'm just going to kind of go real fast and highlight the extra terms. So we're going to sort of get a VN, that's just the terminal costs like we're used to, and we're going to back up one step. I'm just going to kind of write that back up in general. So we're going to do this thing. And remember, typically we write this down as min over u of the action value function, right? But here, the tweak is it's going to be min over delta u max over delta w. So we're going to solve the mini-max problem over u and w backward, right? So one way to think about this is you can really think about this as like it's exactly the same, but we're like, you could think about it as, you know, treating W as just like a more control inputs, right? So you could actually get most of this by like imagining you stacked U and W and made that a new control input. And you would look essentially the same, but you're minning and maxing, right, over the two pieces. That's the only thing that changes. Okay, so this thing, we're going to just write out the pieces. So this is the constant piece. Then we're going to get the gradient terms. Then we get a bunch of Hessian stuff. And we get, so here's all the sort of diagonal terms, I guess. Then we're going to get all the cross terms. Okay, so that's the whole thing. And we're going to do the exact thing you expect, no surprises. We're going to just take the gradients with respect to both u and w and set them equal to 0. So it looks pretty much exactly like we did before. So we'll get the following kind of stuff. So partial of that thing with respect to u, but again, we're just going to pick up some extra terms. So this is kind of what it would have looked like in the standard sort of ILQR setting. You would get this stuff. And now we're going to pick up one extra term with w things in it. So we set that equal to 0. We're going to do the same thing again, but for the w's. Okay, so that's the whole thing. And what we can do after this is solve for the delta u and delta w, from here. So this is all pretty straightforward. So there's the delta u, here's the delta w. So the interesting question now here is, in this step that I just took, is there any notion of min or max? Like, it looks like I did exactly the same thing for both the u's and the w's there, right? I just set gradients equal to 0. So how do I know if it's a min or a max or whatever? How do I know I'm at a saddle? Anyone have any thoughts? Yeah. So what has to be true for this to be the desired saddle point?
Means the dimension of the number of negative eigenvalues, the dimension of the number of positive eigenvalues.
Other way around, but yeah, close, right? So okay, so yeah, so this, we're saying it's a saddle point, but what we're doing here is essentially Newton's method, right? If you remember way back to the very beginning, we had this whole idea of like Newton's method is just doing root finding, right? And to have a saddle or a min or a max or any of these things, the gradient equals 0 is just a necessary condition, not a sufficient condition, right? So here, yeah, at the saddle, that has to be true, but that's not enough. In addition to this, you have to have these Hessian conditions be true. And ultimately what that comes down back to is like, if I look up here at the action value Hessian, right? Basically this action value Hessian, essentially the parts of the Hessian corresponding to like the X's and U's up here, these guys need positive eigenvalues. And the part corresponding to the disturbances, this W guy, this guy has to have negative eigenvalues. So that's what it should have. It may get messed up like we've seen before, and you might have to regularize this. It looks basically like the primal dual situation where you've got to regularize some parts of this guy positive with positive, like a positive identity, and some parts with a negative identity weight to make sure that it's doing the right saddle point thing and sort of heading in the right direction. And that can get messed up. So that's that comment. So where did this go? Cool. So let's write that down. So you need GUU strictly positive definite and GWW strictly negative definite for that to all work out. Okay, cool. So there's that. And then note here, right, these two players, the U and the W, they depend on each other. They're coupled, right? So like the U I choose depends on both the state and the disturbance at that time step. And that's kind of annoying and not what we want. So what we're going to do is basically plug these back into each other and play some manipulation games and eliminate the cross-dependent terms, which you can do. It's like simple algebra. Trust me, as I'll say you do this. And then once you do that, you get the following sort of feed forward and feedback situation that we're used to. So you're going to get a delta U equal to a feed forward term, a constant, in other words, and then a feedback term, K delta X, just like we're used to. And these are going to look like the following. So you're going to get, I'm going to write this out sort of to emphasize what, the differences are between the stock version of ILQR. Okay, so that's the feed forward term. That's the feedback term. And apologies if my little squiggles are hard to read at the bottom there, like the U's and the W's. I am sympathetic. I'll send you the real paper so you can like parse that instead of my scribbles. The LaTeX is much better, I realize. Okay. There's that. Okay, so now if we look into this, this stuff is exactly the same as stock LQR, ILQR. Yeah. UW, yes. Yes. Yeah, sorry. I'll post the real thing. You can look it up. It's a little nicer. So these things, if we go back to like the standard LQR, ILQR stuff, these terms in blue are the standard things. So if we did no robust stuff at all, we get that answer. And then these terms in red are sort of the new robustified correction terms, if you like. So let's write that down. So question, is there like a limiting case here where those robust terms sort of drop out? Yeah, I mean, that's the intuitive thing, right? So how do I get no disturbance here? So we didn't really talk about this yet, but the way to get this to drop out is to have, actually, this should be a WW. This is horrible, sorry. So these cost Hessians that get inverted, basically those GWW inverses, you want like, if GWW, aka the Hessian of the cost with respect to the disturbances, if that's really, really big, then those GWW inverses are going to go to 0 and those terms are going to drop out. So what this corresponds to is like, if I imagined my cost function, if I have like essentially, if I imagine the two players setting, right? If I think about W as the control inputs for the adversary, if the adversary has an extremely high cost on its controls, right? So if player W, like if you imagine having a quadratic weights, like in an LQR setting, if I have like a quadratic cost on W, i.e. the W player has some cost of acting, right? If their cost of acting is extremely high, then that means they're not going to act very much, right? And so in the limit of having like a super high cost on the W player's actions, that GWW basically goes to infinity, and then the GWW inverse goes to 0, and all those robust terms drop out, and you get like that limit gets you back to standard like IOQR non-robust land, just to, so we're all thinking about this the right way. Does that make sense, everybody? Cool. Okay, so that's the sort of U player, and you get very, very similar things for the W player. And we're going to write this as just different letters. I'll use L, I guess, since we're not doing filtering, and I can, sorry. So basically the interpretation here is you have these two players, they're sort of fighting each other. Each of them has a policy that's a state feedback policy, right? So they each have a policy that's just a function of the state, and they're both doing the best they can and sort of duking it out, right? And then you land on this equilibrium for both of them. And so this guy, similar stuff. I'll just write this down real quick. But yeah, it sort of has a symmetry where it kind of mirrors they mirror each other with just the U's and the W's flipped.
If GWW is opposite designer, then we can suppress noise anything.
So yeah, the idea is I mean, it depends on your model of the world, right? Like the idea is that like this is supposed to capture some like uncertainty in your model or in the environment or something, right? Right? So ideally, it's not really a made up quantity that's coming from the designer. It's something that like actually reflects physical uncertainties in the world or the environment or the model or whatever, right? But in practice, yeah, you're picking this thing, right? And it's a bit of a tuning game. That said, yeah, so we're doing this sort of, LQG-ish approximation of this thing where it's all quadratic. But I kind of mentioned before, right? Like the sort of maybe more correct way of getting at this is rather than like costs on W, say, you want to maybe think about it as bounds on W. So i.e., this stuff would really be showing up via constraints on W. Like you could put box constraints on W, right? And say, okay, W can be anything in this range. There's no cost on it per se, right? That's kind of more the flavor that is typical. And here, if you were to really do this and you were to sort of do it that way and try to like do it with just bound constraints on W, you would, if you were to do like sort of augmented Lagrangian, for example, to sort of put the bounds on W, ultimately those augmented Lagrangian constraint terms would boil down into gradient and hashing terms in this expansion, right? So we're clear on all that. So you can do all those things. There's lots of layers to this and it can get quite complicated, but the basic idea, you can still kind of get at this in this kind of linear quadratic LQR type viewpoint. Okay, cool. So we get these like feed forward, feedback terms for both players. We can then plug in delta U and delta W back in to our action value function to get our new value function or cost to go. So that's all kind of the same stuff. And so you're going to get like a new V. And we're going to write it like we've done in the past with the gradient is little p and the Hessian is big P. And then little p is going to be the following thing. And that's the sort of standard LQR stuff. And then you get the extra term with the W player making the cost worse. And then the Hessian, yeah, similar idea. So I guess the takeaway message here, I think, is that like knowing the basics is really, really good. Like you can get really far by just being clever and knowing LQR really well. You can do stochastic things, you can do robust things, you can do nonlinear things. Cool. Okay, so that's pretty much the end of the day. This looks, once you get to here, right, the action, so the value function, it looks exactly the same as stock ILQR, right? It's just a function of X. And the way to think about this is, right, like you have a U player and a W player, and they're fighting each other. They each get a policy. You optimize those policies, and that's kind of the idea. Okay, yeah. So then a few comments, right? The biggest difference versus standard DDP that we've seen before is that the action value Hessian is no longer sort of positive definite. It's what we call quasi-definite, right? So it's got a known number of positive and negative eigenvalues. And it should have sort of the stuff corresponding to X and U should be positive. So that's a min, and then the stuff corresponding to the W player should be negative, i.e. a max. Cool. Let's see. And then sort of taking that idea into how we specify one of these problems. When we write down a cost, say we're to write down a quadratic cost function for this thing. The Hessian with respect to W should be negative definite. So if I had something like the following, like our standard kind of LQR sort of thing. So maybe this. And I don't know, this is slightly terrible notation. I'll like use a big W for this, I guess. And then our terminal cost on the state. You would want the Q, the QN, and the R to be positive definite. Well, I suppose semi-definite for the Qs technically. And then you'd want this big W to be strictly negative definite for this to kind of make sense. Similarly, if I need to regularize this thing to make sure I'm getting a saddle point, so we'd end up regularizing G in the backward pass. We do the same sort of thing you would do on a KKT system. You'd have sort of a positive regularizer for the XU stuff and a negative one for the W stuff. Okay, and then interpreting that cost function a little bit, we've got, so if the W there is small, the norm of it's small, right? So like the diagonal elements are small, whatever, of that big W, that cost term, that's gonna allow large disturbances, right? It means think about that as the cost on control inputs for player W, right? So if that Hessian for player W, big W, is small norm, it means it's not expensive for player W to exert large actions, right? So that sort of interpreted in a robustness kind of way. This has, you say, large WKs then, and that would, if you're thinking about this in this kind of Minimax robust control context, that would tend to make the resulting policy more robust, right? It means it's going to have to tolerate, it means that player U is going to have to tolerate larger disturbances, right? So kind of conversely, a large big W means it sort of penalizes the WKs more, and you would get ultimately, less disturbances in the answer, and you would end up with a less robust policy, right? And kind of as we said, when we were looking at that cost function, if you kind of stare at that for a second, in the limit, as kind of the big W goes to negative infinity, we get back standard DDP. Okay. That's the whole thing. Any questions about this? Yeah.
So there had W elements towards the bottom. How is alpha fitting the GW?
Yeah, so the idea is that the whole G, by that whole G, I mean this whole Hessian here that I've written down blockwise. So this guy, this whole matrix is G.
Okay.
So the positive alpha corresponds to the top block, yeah, with the GXX GUU. And the minus alpha goes into the GWUW term. Yeah, so it's a saddle with respect to, right, it's a min with respect to X and U, and it's a max with respect to the W's, right? So that's the minimax thing. It's a saddle point, and it's got a sort of, it's a minimum in those two sort of sets of directions and a max in the other sort of W directions. And you're trying to make that, sort of show up the right way in that matrix. And that's if you need to regularize because things get messed up numerically. So so there's lots of ways to regularize. The easy way and the kind of standard way is to basically add this multiple of the identity thing. There are technical requirements on the cross terms to have a positive definite matrix, but it turns out if you just kind of like jack the diagonal elements up, that takes care of it eventually. And that's kind of the easiest thing to do. You might be tempted, for example, to just do an eigen decomposition of this guy and then like jack up the eigenvalues and put it back together. The reason we don't do that is because it's more expensive. So on a large problem, like taking a full eigen decomposition is quite expensive. So it's cheaper to just crank up the diagonal elements, and effectively does the same thing. And since we're approximating it anyway, there's not much point in like doing the more expensive thing. All right. Yeah.
And go down where you have D and in the top of red brown. So the term in the bracket, those terms have to be positive or definite, like G plus.
The stuff, sorry, in the delta U, delta W? Okay, so the deal is, going back to like the positive definite thing, it's really the GUU, the thing that I'm inverting in front of the box, that has to be strictly positive definite. And the GWW that I'm inverting there has to be strictly negative definite.
Okay, that got like the terms inside they can mean anything.
They matter a lot less. Yeah. They can't quite be anything, but almost. Yeah, like in terms of like defining the kind of equilibrium you have, it's really all about the diagonal blocks. Those are the ones that matter the most.
And another question is when we are minimizing with respect to U, why are we considering the eigenvector of X?
So let's see, what's the right way to say this? So you're minimizing here instantaneously in the backward pass with respect to U. Technically speaking, like you can, so the cost with respect to X doesn't have to be strictly positive definite, but it has to be at least semi-definite, i.e. it can be flat, but it can't be negative definite. The reason is, right, if it were the other way, that would mean like, I mean, you could write that down, but it would mean that like the controller would end up pushing you away from the goal, right? Because that's lower cost to push you out away from like X goal or the origin or whatever, which is not what you want, right? Does that make sense?
Yeah, so why don't we minimize it with the U and?
We are. This is going back to like the dynamic programming sort of idea. You are actually minimizing, like we are solving the problem that I wrote down up here, right? This is the problem we're solving. That question is several weeks ago when we did sort of the, dynamic programming, LQR, ILQR stuff. This is like the Riccati solution to that problem, right? Which is like this kind of clever back substitution game that we played. Remember, we wrote the QP down and did the back substitution thing. So we're getting the solution to the QP, right? But we're getting it via this clever back substitution trick. And what you're really doing, if you want to think about it, you're really kind of getting a parametric solution to this problem in the form of, like when I solve LQR, right? I get a feedback policy that's a function of X. So what you're really doing there is getting like a parametric solution to this minimization problem where for any given X, I can plug it into the policy and get the optimal XU trajectory, right? So that's like, does that make sense? So it's a very clever, cool, like dynamic programming control theory thing. Ultimately, you are minimizing with respect to both X and U, but there's this very nice structure in there that lets us solve it with this dynamic programming trick and get this nice result. So that was several weeks ago. Yeah. If that's not clear, right, like we should talk, but we're just doing the same trick again. We're doing the Riccati dynamic programming thing, but now on this Minimax version of the problem. And I'm basically just showing you the delta from classic DDP to this Minimax robust case. And basically what happens is you get, Minimax things showing up when you do the action value stuff in the back pass, but otherwise looks extremely similar. And at the end of this, you end up with a policy, a U player policy, which is what we had before, and a W player policy, the new bit. And you get sort of new terms in the cost, right, that show kind of how the players interact and this kind of thing, right? Okay. Everybody cool with that?
So you always have bounds on the norm of the W claim, right?
I mean, not always, but that is the typical setup. So like in robust control theory, the standard thing, which is really for mathematical reasons, is to assume some sort of bounds on the W's. Otherwise, you can have like arbitrarily terrible things, and then the problem sort of doesn't make a lot of sense, right?
You always have to solve constraint DDP.
You don't always have to. In fact, this Minimax DDP paper that this is from, that I'll show you, they didn't have control constraints or sort of constraints on, and what they did instead was effectively have like soft constraints by modeling it as a quadratic penalty in the cost function. So they had like a quadratic cost on W's effort, right? So that gets you a bounded solution, like that gets you a tractable solution and the math works out, but it's also, this is a bit of this isn't the standard thing, I would say. This is because this is in line with the stuff we've been doing. So it's a nice little intro to the topic, and you can get at these things with the stuff we were talking about, but most of the like 80s, 90s vintage, like H infinity stuff are kind of from a different viewpoint and using a different set of tools. But yeah, like the more standard thing in the field is to assume bounds on the W's, norms, boxes, polytopes, whatever, right? Like stuff like that. And that kind of makes this whole Minimax thing make a little more sense, right? It's like, okay, if I can have any W from this set, then like, I'm going to pick the worst W that you could possibly pick in the set. And then, the controller now has to do the best it can, given that worst case sort of stuff. All right. Anybody else? Okay, so I'll just like quickly show you. I don't have a code demo for this because I did not code it up because I was lazy. I tried and then I ran out of time. But I'll show you. This is the paper I was talking about. This is from Chris Atkinson from here. So cool CMU connection, about 2003. And what they did exactly this. So this is, you can see the derivation in nice LaTeX form instead of my scribbles you want in here. Although I think there's some steps that got skipped in here. So I filled in some more details that weren't in here. And they did this in the context here was a simple biped. They actually did this on hardware. So it was a little two-legged, kind of robot that they were trying to make walk. And the demo was they basically had like some hand-tuned PD controller, and it's trying to balance and walk, and it would face plant because of disturbances, et cetera. They did standard DDP, and it actually did even worse than the hand-tuned stuff. And again, face planted after so many steps. And then with this Minimax approach, they got like a really robust walking policy out of it that was robust to kind of errors and disturbances. And so therefore was able to walk a lot farther before falling over. So it was kind of the original kind of thing from the paper, kind of fun. Yeah, check that out. Kind of cool. I'll post it. And then I wanted to tease actually. So this is, again, this is the DDP thing. And we've seen a lot in the course, right? Like this kind of, for these nonlinear problems, you can do DDP, LQR stuff, or like this collocation stuff, right? So this is kind of the DDP approach to this. A very similar but collocation version is a paper I did as a postdoc about 5 years ago. We called this DIRTREL. It's sort of like a DIRCOL. Here, going back to this idea of typically you assume bounds, we assumed ellipsoidal bounds on the disturbances. And we assumed an LQR feedback controller. So it's very much like the DDP style idea, but like a collocation version of it with hard ellipsoidal bounds on everything. Yeah. Means that you say like W can be anything inside this ellipsoid. And you're doing the Minimax thing, right? So you're saying it can be anything in there. There's no cost on it. So you pick the worst one or whatever, right? Within the set. And then the controller has to do the best it can. So we did that. We did this on some fun things. So if you want to see the collocation version, it's in here. So we did like Carpol with all kinds of uncertain stuff and showed that like it doesn't swing up successfully, with standard stuff. And then if you do the robust stuff, it works. The most fun example in here was a quad rotor flying through trees with wind gusts. So you don't know the wind gusts beforehand, right? So the thing that comes out of this is kind of cool. So red is the trajectory you get with like the vanilla version of this, where it just takes the shortest path essentially. The problem is your quad rotor is under actuated. So you can imagine if I'm like weaving between the trees, I'm flying really close to the trees. If I get hit by a wind gust, I can't do anything and I'm going to hit and crash the tree, right? And then if you kind of jack up the disturbances that it has to account for, you start getting these new trajectories that swing way wider around the tree. And the kind of really interesting thing is this thing's under actuated, right? So with a quad rotor, say I'm flying, like this, as I skirt past a tree, I can't, if I get blown this way, I can't do anything, right? Because it's under actuated. I would have to actually change my attitude to get a thrust in the opposite direction to not crash. And the really interesting results out of here is that it starts to like take the corners where it's cheating its attitude a little bit. So it can like have thrust in the right direction to counter a wind gust that would crash it, which is kind of really cool. So you get like really interesting emergent behaviors out of this that are super fun. Anyway, that's it. So there's cool ideas. Oh, this was a fun one too. It's like a milk jug with fluid slosh that you didn't have a model for. So you kind of bound the fluid slosh behavior, try to get it to like, wave the thing around with an arm. Anyway, cool. That's it. Yeah. We're done for the day.